Hi, welcome back. Today we're going to discuss the beginnings of what's called Gauss's law for electric fields. And I'll go ahead and share my screen. So, a few things that we need to discuss before hopping into Gauss's law is the concept of flux, which the video prior to this one goes through fairly thoroughly. And so flux is essentially a measure of field lines through a surface. In this case, electric field lines, but there can be other kinds of fluxes besides the electric flux. And of course, we learned how to write it for the non-calculus applications as the E field dotted with the area vector. However, this does not work for surfaces that are curved in certain ways, and it does not work when the electric field varies given where you're at on the object or on the surface. So the more official way, the way that's always correct to write it is like this. The electric flux equals the surface integral of the electric field. So the two integral signs represents that I'm integrating over a surface or an area, and dA, of course, stands for a small area. And the E field here might be a function of that area. So, like maybe for this surface over here, the E field is different for this area than perhaps it is for this area. So that's perfect case for when we would need integration. All right, next, let's talk about what an enclosed surface is. So when I think of an enclosed surface, I think of if I were to put an object in that surface, the only way the object could leave the surface is if it broke a hole in it. So in other words, over here, I have this sphere, and let's say that I put an object in there. The only way for this object to escape the volume inside of this surface would be for it to break through the surface and create a hole. So this would be a good example of an enclosed surface. And with enclosed surfaces, the dA vector is always pointing normal to the outside of the surface. So you see I have these dA vectors drawn, and they're normal to the outside of the surface. And so if the flux is the double integral of E dot dA, then that means that if the electric field is parallel with dA, then that would give us positive flux, right? Because E dot dA is E cosine theta dA. Cosine of 0 is 1, so that would give us positive flux when the E field is leaving the surface. And when the E field is going into the surface, that would give us negative flux. So positive flux is leaving the object, the enclosed surface, and negative flux is entering. All right, so let's talk about Gauss's law. So first, we're going to take a look at two different cases here over in this enclosed surface. We have a charge inside the surface I'm calling Q1, and we have a charge outside the surface I'm calling Q2. So let's start by focusing on Q1. So let's draw a few electric field lines, of course, emanating radially outwards. And we see that there's definitely, assuming this is a positive charge, if it's negative, the arrows would point in and terminate at Q1. But we're just going to focus on positive charges right now. So we can see that there is a positive flux created through the enclosed surface by this charge. Of course, if it was, say, a negative charge, then there would be a negative flux. Okay. So what we've found out is that if you have a charge inside the enclosed surface, there is a flux created or a net flux that occurs due to the charge inside the surface. Now taking a look at Q2, let's say it's a positive charge as well. We'll draw a few field lines. just enough to get the idea. Okay, so it looks like we have some field lines that are missing the enclosed surface entirely. We also have some that are entering the enclosed surface, and every line that enters the enclosed surface must leave the enclosed surface. So this field line enters the surface here and leaves the surface there. This one enters here and leaves there. So it seems as though every field line that enters an enclosed surface due to an external charge will leave the surface. And so you could think about that as this is negative flux right here because we're in the field line's entering the surface, but then over here, the field line leaves the surface and has a positive flux. And so without going too much further in, basically this negative flux created by this field line and this positive flux created by the field line leaving the surface, they net to zero. So in other words, the net flux through an enclosed surface caused by field lines from an external charge is zero. And you may be wondering, but the further away, the weaker the field, right? So wouldn't this side over here have a weaker field and this side would have a stronger field? And that is correct. But also notice that you remember flux is the, let me write it down here, simply written just for relational purposes. It's essentially E times A. And so you'll notice over on this side where the field lines are entering, the area is much smaller than where the field lines are leaving the surface over here. So even though the E field strength is weaker on this edge or on this side of the surface, there is greater area. And so even though E goes down, A goes up. And so there's a compensation there. So Gauss's law is pretty clever invention. And in written form, it's this right here. And it states that the electric flux through an enclosed surface is equal to the charge enclosed, E and C, charge enclosed, so charges inside the surface, divided by a constant, the permittivity of free space. All right, so the only difference is you remember when I wrote flux over here, I had the double integral sign. That's the general case. Over here, I have it written with the double integral sign with a circle around it. And that circle is used to indicate that this is an enclosed surface that we're integrating. All right, so I'm going to end this one for now. I was going to go on to an example of uses of Gauss's law, but I think I'm going to cut off the video here and then make one specifically for that. So I hope this was useful for you and hope to see you next video.